Hello everyone, welcome back to Alkaline Hydroxide 784, and today in the physics series we will be covering the current of electricity. Actually my voice is already kind of messed up after talking for 40 minutes earlier, you know why. Okay, anyways, so now once again I'll be looking at the learning outcomes, and I hope this doesn't last for 40 minutes, so yay. Okay, cool. The first one, electric current. Okay, well, the first thing that you need to know is what electric current is. And the current is basically like the speed of the charge, basically. So it's the rate of flow of charge. And that's why, if you look at the equation, Q is, well, charge, I guess, and current is I. So Q is equals to I times T. And vice versa, you can say I is Q over T, so the amount of charge flowing through per second. That's pretty much it. Okay, so the second point, for current carrying conductor, we have this thing called I equals to NAVQ. The reason why, we will cover it right now. Okay, so if you look at a conductor, you can imagine it as a cylinder or a cuboid or whatever. You know, it's a 3D object. It's not some small, it's not like a line or something. It's a 3D object and it has an area, surface, I mean like the area, cross-section area kind of thing. And that cross-section area is the big A in this equation. And then if you look at the speed of the so-called speed of the charges in the sense, which would be v. In this scenario it is called the drift velocity. It's the number of number of electrons or whatever is moving per second, I guess. And n is the number density of charge carriers, and q is the charge of one, wait, what? Okay, the charge of one electron or whatever, or the charge of that thing that's moving in a sense. So in this scenario, the reason why it's written as I equals to NAVQ is, if you look at the original equation, I equals to Q over T, the big Q is like the total number of the total charge, and that would be equals to N times Q, right? So and the area is, okay, so we are looking at the amount that's passing through a certain cross section in a sense. So the area is quite important, and the velocity is kind of like the distance over the time. So the area times that distance is the volume, kind of, yeah. And the over the time will give you the over the time in the original equation. So in this scenario, we're looking at I equals to the so-called volume times the number. The volume is there because we have the number density. So the volume times the number density just becomes the number itself. And then the number times the Q becomes the big Q. And the remainder thing that's there is the over time, and therefore you get I equals to Q over T. And that's why I equals to N big A V Q is a valid equation. Yeah, I hope you get that. So then the next part is record and solve problems with using a bunch of equations. Yay. Wow, this is like really, I don't know how to explain this. It's just, if you get a question then you use this equation. That's pretty much it. So the equations you have are Q equals to IT, which I guess is pretty straightforward. Charge is current times time. So if you need to calculate charge, you use this equation. And then the next one is V equals to W over Q, which is potential equals to the work done over the charge. The reason for this is because if you think about it, potential is related to potential energy, right? So if you remember the last chapter, and potential energy, if you want to make it into potential, what do? you kind of remove one of the R from the, wait, is it, yeah, you kind of remove one of the R from the denominator. And in this scenario we have work done, so energy is work done over time in a way. Yeah. And Q is, well, the charge in this scenario. So but Q is equals to ITs. So if you think about it, it's like work done over IT, right? So but the I is, well, current in a sense. It's like a speed of some sort. And okay, I don't know where I'm going with this, but you get the idea. Yeah, you get the idea. I guess I'll write it down, and it'll make a lot more sense if I write it down. So if you have this equation, you can solve problems with it as well. So just remember that potential is equals to work done over charge. Yeah. Okay. So it's like the work done per charge in the sense. Oh yeah, that makes sense. It kind of relates to the definition of electric potential. It's per charge, unit charge. Cool. I think you understand. We get it now. Okay. Now let's move on. Okay, what is this? Sorry. The difference between potential energy and potential is the one of the Q. Oops, never mind. That's why you're dividing it by Q, because the work done is kind of like energy in a way. Yeah, okay, never mind. The work done is the energy, and then you're dividing by Q, then you get potential. Okay, cool. Let's move on. I'm sorry for making myself a fool, but never mind. Okay, so the next one is power equals to potential times current. So now that we know that potential is work done over charge, then if you think about it, charge is IT. So if you cancel out the I from the denominator and the numerator, you will get work done over T, I guess. Yeah. And that is power, because work done is energy. Okay. And then the next one is P equals to I squared R, which is just just shuffling things around, because in this scenario we know that V equals to IR, because you've heard this many times before. And since V equals to current times resistance, you can actually do all that variation. P equals I squared R, then P equals to V squared over R. And then we have the V equals to IR equation. Okay, so if you look at all of these equations, what can you use them for? You can use them for, those questions with the circuit, then you need to answer that. Or if you're looking at a word question as well, it may ask you to do stuff that requires you to use these equations. So please remember the equations. Like, that's the easiest way to get marks for those kind of questions. Remember the equation and then use them properly. Simple. It's as straightforward as that. So the next point is about the IV characteristics of various electrical components. This is pretty interesting because, finally you see some visuals in the sense. So the stuff that we have here is an ohmic resistor, a semiconductor diode, a filament lamp, and a negative temperature coefficient thermistor. Okay, so in an ohmic resistor, aka a resistor that follows Ohm's law, which is V equals to IR, you will see that the IV graph is basically just a diagonal line that looks like the X equals to Y graph kind of look, in a sense, because V equals to IR. That's pretty much it. Simple as that. So the R is the gradient of the of the graph based on whether it's I or V in the Y or X axis. It could be either R or 1 over R. So that's the gradient. It's very simple. It's just a straight line. If it's a semiconductor diode, we would so for the other stuff, you can see that there's a bit of difference in how the resistance works, because because each of these has their own variation in resistance. In a in a semiconductor diode, the diode tends to have a direction of charge that it favors, or current for that matter. So it will favor current in one direction but not the other. So in other words, if you were to draw the axis in the direction that is negative to the diode, there would be hardly any current, or like there'll be hardly anything going through it in a sense. So the resistance is extremely high. And on the other side, it would be quite normal, and the resistance, yeah, the current that you get is very, you know, large in the sense. So since the IV graph that you're drawing will be having the gradient of 1 over r, you will be seeing that on the negative side the 1 over r is really small, so it's almost 0, and the graph will be almost towards the axis, the x-axis, and on the other side it would be going normally, and it will shoot up almost vertically but not exactly vertically, so it's like an asymptote there. But please don't draw an asymptote lah, just make it look like it's going really high up in a sense. So that's how a semiconductor diode is supposed to work, but in an ideal sense. But a real one, obviously you won't have it shooting upwards directly, but more of a bit more gradual, I guess. Okay, so a filament lamp. A filament lamp is the non-ohmic resistor. So you just need to draw the same line, but it won't look like a line anymore. It will look a bit more like a curve. So since it is a filament lamp, as the temperature increases, the resistance will increase, or like the potential increase, the resistance will increase in a sense. So as the resistance increases, the thing will go down. Like, sorry, the gradient will decrease if you're looking at the gradient being 1 over r. So please realize what the gradient is in your graph lah. If your graph is actually swapped, like the I and V are swapped in the axis, then it will look a lot different in a sense. So please be a bit careful about that. But if you're looking at 1 over r as the gradient decreases, so in the positive direction it will go like this. I'll draw it out. The negative, it'll go the other way. You get the idea. And for the negative temperature coefficient thermistor, the resistance decreases when the temperatures increase. So it's the opposite of the lamp. So yeah, that's pretty much it. I hope that works. So so for the temperature negative temperature coefficient resistor, well, yeah, as I mentioned just now, that for negative temperature coefficient thermistor, the resistance will decrease when the temperature increases. So that's, if you look at the of H, sketch the resistance temperature characteristic, just write that. Just draw that, like the resistance decreases when the temperature increases. Simple as that. Nothing crazy. Okay. For I, we are looking at equation resistance equals to rho L over A. Is it rho or what? I don't know. Yeah, it's kind of like density, I guess. Okay, so sorry. Actually, it's not really density. It's like it's it's the conductivity. Yeah, it's actually a conductivity. The conductivity is like the, wait, what? Conductivity. Okay, never mind. I don't know what I'm saying, but okay. So if you're looking at L, you know that for any conductor, the resistance increases when you increase the length, because there's more stuff for the electrons to go through to reach the destination. But when you increase the area, there's more space for the electron to go, so it will decrease the resistance. The reason why I'm saying it like this is because you imagine electrons moving through like water flow. So if the resistance is higher, there's lesser water flow in the sense. And that's why for the equation you'll get R equals to PL over A. So the P or the rho or whatever you call it would be a value that you can get as data in your question, and you can use it to do this equation. So if they give you some values, then you can use it to put in your equation. So the rho is actually called resistivity. So it's kind of like a base unit kind of thing that you can augment using the length and the area. Yeah, that's how you modify it. And that's how you do this equation, I guess. There's nothing much to do here. Just type some stuff in the calculator and you get it. Okay, cool. So the next one is EMF and potential difference. Okay, so there's a difference between the two of them. So the the electromotive force is used with regards to a battery. So the battery has a electromotive force of a certain amount of volts, and the electromotive force is energy used to move the electrons around, like to move the electrons around the circuit, or to generate the current in a sense. And the potential difference is so so the electromotive force would be like the energy required to do it. The potential difference is the energy, um how do I say it? It's like the work done is different in the sense. So electromotive force is the work done to actually generate the current, and the potential difference is the work done to dissipate it in a sense. So the work is actually done when it comes to potential difference, but work is negative work is done in a sense, or you're generating some kind of, you're converting the energy from chemical to electrical energy, and in potential difference you're converting the electrical energy into other forms of energy like heat or sound or whatever it is, light energy, anything. So that's the difference actually. And then the final learning objective is the understanding of the effects of the internal resistance of a source on EMF of the terminal. Oh, okay. uh Sometimes the battery has its own resistance. So that resistance in the battery is usually represented with a small r in the question, and or in your working, I suppose. So the internal resistance will also end up doing some, converting some electrical energy back into heat energy. So that means that the overall power output will be lesser, in a sense. Like the useful power output will be lesser lah, but the overall output is the same, but the useful power is lesser in a sense. And so the terminal potential difference would be what you do between the battery, and that would be equals, so if you think about the circuit, in a sense, you draw the battery and you draw like a light bulb or something, and you say the battery is 9 volts, but the potential difference across the light bulb is 8. So that means that 1 volt is being used within the battery itself, and therefore the EMF of the battery, which is 9, is equals to the internal resistance times the current on the circuit. So that will and eventually give you 1 volt, I guess, and the plus the potential difference of the light bulb. So just use that logic to solve the equations that you get based on the circuit and based on what is there in the circuit. So do remember the equation that is relevant to this whole thing, which is the how the current and the potential potential difference and resistance change according to series and parallel connections. Yeah. So I think we'll be looking at that more in the next chapter, but this is how it works when it comes to internal resistance plus the terminal potential difference. Yeah, cool. I think you're done. Yeah, you're done. I guess a lot of this is really just equations, and you need to know where to use equations. So I think it'll be pretty obvious. Like if you see a question is about electricity, you can already kind of narrow it down. And if it's about a circuit rather than some weird charge floating through mid-air or something, then it's more likely that you're gonna be using these equations because there's a circuit involved, or there's like or if it's some kind of resistor, or it's talking about resistor, or if it's talking about one of those, what is it, the transistor stuff. Basically anything that's related to moving an electricity around, or like moving a current around or doing something like that, then you had to probably use one of these equations. So that's how you figure out where to use the equation. I hope you found this video useful despite my brain getting tired after talking for 40 minutes for the chemistry episode and another 20 minutes here. But yeah, if you found it useful, please press the like button and subscribe. And with that, I would like to say thank you and bye!